The role of craters in the solar system through impacts or electric discharge. Side by side, the two theories have potential in telling us something about celestial bodies we observe today, but the sources and timeline of events differ. Large craters, such as Tycho crater, with a diameter of roughly 85 kilometers, are considered to be complex craters in the solar system and don't occur at present date in either theory. The supposed impactors or electric fields that would have pulverized or electrically machined surfaces are not currently available for study. The lunar surface is covered in these types of craters, well, half of it at least. Some examples are Ohm crater, Copernicus crater, and King crater. Some specific features of these larger craters are terraced ridges and central peaks. When considering impact theory, we would suggest that impactors are traveling at hypervelocities upon impact. The sudden collision of the two bodies produce extreme pressures, compression, and shock waves. As the shock wave travels outward from the impact, it vaporizes, liquefies, and fractures the impact site. The shock wave also causes refraction in the crust, excavating the crater and forming central peaks and terraced ridges. This particular process, in which the craters are formed, is extremely energetic throughout the crater and relies on hypervelocity objects. The terraced ridges and central peaks observed do not remain intact with impact experiments dropping or propelling objects onto surfaces. On the contrary, craters formed through electric discharge can be observed producing terraced ridges to scale. When material is caught up in the electric field and machined away, the walls of the crater will collapse inward and slump, producing similar terraced ridges. In contrast to impact theory, a discharge can machine specific areas of a surface and not the whole crater all at once. A filament can travel, allowing for dynamic machining that forms other types of features that can be used as analogs to those found in the solar system. At any point during a discharge, the crater can present a number of specific analogs: rimmed craters, straight-edge craters, crater chains, central pit craters, and terraced ridges. The electrical hypothesis has a lot of potential for explanation, and scientists have experimented with its possibilities for decades, as opposed to a series of untested events that have to occur to form one feature, the terraced ridge, while lacking support for other peculiar features as well. It can also be seen in low-pressure discharge experiments containing silica that large eruptions can occur over the surface of the silica, obscuring any previous formations with ejecta. When looking at surfaces of rocky bodies, craters that are covered in ejecta or smoothed over are considered to be vastly older. I think it's also possible that subsequent electric discharges could produce obscure-looking craters, with the final discharges that occurred forming sharp and defined features. This all happening in a short period of time. The craters are likely indeed older, but it's possible not by much. During the experiments, a major factor in crater formation are the states of matter, specifically liquids and gases. Most samples used will contain air and moisture from the air. In other samples, ice was used to provide a source of liquid water. The vacuum pump removes air and gas from the chamber and within the soil, causing a low pressure throughout the experiment. The vapor pressure of water is such that in these low pressures, the liquid water readily vaporizes by boiling into the vacuum. This process of introducing gaseous molecules from the water will increase the size of the craters because of the rapid vaporizing. The filament can move from crater to crater as new gases join the atmosphere. It's my personal thoughts that the filament helps to expose and release gases from the surface as the excited plasma is a better conductor and the current is conducting the path of least resistance. When liquids are vaporized, they continue to change where the path of least resistance is available, and when becoming part of an electrical current, they will move in the direction of current flow, pushing silica out of the way, like an ionized wind. I also believe that the soil itself will conduct current flow, this resulting in silica molecules bonding together. As in an electrical current flow, the outermost electrons of an atom or molecule will exchange electrons with other molecules' electrons. It's possible that's how the silica molecules would bond together, forming a fulgurite on the cathode, as a result of conducting current with each other. Another subject to consider are ejecta blankets around craters. Nearby surrounding terrain of a crater rim is often uneven with clumps and mounds. In electrical experiments, ejecta will stream out from the crater, producing fountains of material that could be the source for the lumpy terrain. As moisture is fully removed from the crater, formation will change less, the current having found a suitable path without volatile gases changing pressures and resistance. In these stages are where the electrical theory surpasses impact theory's realm of explanation. With experiments containing ample amounts of liquid water, in the final moments of moisture being fully removed, analogs of jets and plumes seen on moons are observed. Similar bell-shaped features as those seen on Jupiter's moon Io and proposed by plasma physicist Anthony Peratt to be, quote, visible manifestations of plasma arc discharge phenomena, end quote. In dry experiments with no added moisture, analogs to cometary phenomena are observed. This occurs after a crater has formed and the basin begins to burn. It's typical at this stage that a glow discharge will form alongside the cathode filament, producing jets similar to those observed on comets, where jets can be observed in multiple directions, or enormous comas accompanied by a tail.